Hi and welcome to the third video on inferences about means in chapter 22, or 23, excuse me, chapter 23 about inferences and means. Okay, so let's finish up. This is where we ended off on the second video, again talking about, this is a problem number 33 on page 545. Um, and we're going to have some data here that we'll need to put in our calculator. So have your calculator handy, and we'll go into our stat function and type in some numbers so that we can look at the values at the end. Okay, so let's go ahead and get started. In 1998, as an advertising campaign, the Nabisco company announced a 1,000 chip challenge, claiming that every 19-ounce bag of their Chips Ahoy cookies contained at least 1,000 chocolate chips. Dedicated statistics students at the Air Force Academy, no kidding, really did, purchased some randomly selected bags of cookies and counted the chocolate chips. Some of their data are given below. So I'm going to pause here and have you folks do that, or you can pause here if I do go ahead without you. You can pause the video to go ahead and do that. So what I want you to do is go to your stat function and enter in all of these 16 values. I believe there's 16 of them, and into L1 in your calculator. So again, you can pause here. Otherwise, go ahead and listen while I move on. So you do have to have your data in L1. Okay, so once you have that, what does this say about the Nabisco's claim? And then what I want you to do is test an appropriate hypothesis. Okay, so that means that we have to create one, right? So we need to define our parameters and create a hypothesis. So our mean, or our mu, is the true mean number of chocolate chips in each bag of Chips Ahoy. And again, that was a 19-ounce bag, I believe. Therefore, our null hypothesis is that there is 1,000, and alternative is that there's more than 1,000. And our next is to go through our conditions. The sample must be random. Again, it's stated in the problem that it is. The sample distribution should be approximately normal. Now, here's what the graph looks like when you, again, when you have all 16 points. Go ahead to your y equals and you put it on stat plots. So if you don't have your stat plots turned on, you'll have to do that. So turn your stat plots on by second y equals, and then you enter twice if you have a TI-83, TI-84, etc. And you want the default anyway is to have your scatter plot, so it should come out like that. Once you fix your window, you may have to fix your window to show you that data. So here's what it looks like. And then what I did is to show you a box plot to show you hopefully that the values that we need, there are no outliers, which is important. We don't want outliers. We do not want outliers. So to get your box plot to show up, so go back to second y equals, go back to your stat plot. So you want to, where it says type, you want to scroll over into type to the fifth option, I suppose. It's the box plot. Or you can also check the fourth to see if there are outliers. So go ahead and change that and go into your data. Then again, to graph it, you should have a graph that looks like mine. Okay, so what does this tell us? The left graph, the dots, the scatter plot, show us it's fairly linear. And remember, if you remember way back when, linear is good. And again, our box plot shows us that there's no outlier. So the normal probability plot is fairly linear, and the box plot shows there's no outlier. So we will assume that the sample distribution is approximately normal. Then we look at our 10%. So the sample should be less than 10% of the population. The population should be at least 160 bags of Chips Ahoy, which we will assume. Okay, so uh, we know all of those conditions. However, we don't know what our standard deviation is. So since the conditions are met, a t-test for a one sample means is appropriate. And again, it's a t-test. Okay, so we need to make sure that we use a t-test, which means we're looking at our means. We know the mean. And remember, our means, whether we have a sample statistic or actual, since they're the same, we still have that. I'm going to pause here. We're going to need to know what those values are. So I'm going to keep going. We do know n. We're going to have to calculate s. And we're going to assume our 5% or 95% confidence level. So we'll have alpha at 5%. And since we have n is 16, our degrees of freedom is 15. So let's go back to x bar. Now, I don't know if you remember, but you have an option. Since you have all your data in L1, you can go to your stat function and cursor over to calc, and you should have a one variable statistic. If you go ahead and press enter on your one variable statistic, which is option 1, you should be able to get these two values. So we'll come back to those in just a moment. So here's our formula for our t-test. We do know 1000 is our mean. We do know that n is 16. We should have gotten a little more than 1200 for x bar, and we should have gotten a little more than 94 for our s, our standard deviation there. So since now we can calculate the t-value, our t-value, go ahead and do that division out. Our t-value comes out to 10.1053. And again, because we are doing a t-value, you must go to the 4th decimal place. So now we look up our p-value, and we do that again the same way that we do the z. Our probability is equal, or is equal to, when t is greater than, because remember, go back to your hypothesis, t is greater than 10.1053, and we get a little itty bitty value of 2.176 to the negative 10th power, so, or 10 to the negative 8th power. So that means we'd move the decimal place to the left 8 times. That's a very small percentage. So hopefully you understand that it is definitely less than our 5%. So then we would make a decision based off of that value. And this is a one-sided, it's a greater than, so please be careful with our values there. We're doing a greater than. So what happens with these values? So since our decision, since our p-value is less than alpha, we reject the null hypothesis at the 5% level. So therefore, there is sufficient evidence to suggest that the true mean number of chocolate chips in each bag of Chips Ahoy is greater than 1000. Okay. Well, that, my friends, is the conclusion of our notes for the inference about means. I'll see you in class. Good luck.